Okay, so hey everybody. Like you said, I'm Geremy Condra. This is Certainty in an Uncertain World, Gaining Confidence Through Security Testing. And basically what I'm going to be talking about today is a couple of things. I'm going to be talking about what security testing is. I'm going to be giving a couple of examples of archetypal vulnerabilities and how it is that you might test for them. And then at the end, we'll kind of wrap up with sort of a summary of some of the pros and cons of the approaches I've talked about and give you guys some time for questions. Fair warning, if you are a professional security person, you're probably not going to get a ton out of these vulnerabilities because they're not new, they're not novel. But I hope that people who aren't security people will get some value out of it. So let's start out with that first question. What is security testing? And basically, you can think of it as the same sorts of things that you're doing when you're doing normal testing. So you're checking out corner cases, you're verifying high-level properties of your system, various functional properties. But most importantly for us, you're also looking at user behavior. You're trying to emulate the behavior of a user. And in this case, that user is not a normal sort of QA sort of user. You're actually looking at somebody who's an adversary. They're trying to break your system. And they're probably going to try and do it in lots of ways that maybe you aren't perfectly aware of. Modeling this user behavior is the part where a lot of people kind of start falling down. They don't understand the threats, and particularly they think that there's sort of this infinite space of bad user behavior that they have to protect against. And so that's kind of the next question here is, what does this bad user behavior look like? And the reality is that bad user behavior in the real world breaks down to just a pretty small number of categories of sort of real-world common attacks that just get executed over and over and over again. It's sort of a small toolbox that, because programmers tend to make the same mistakes over and over and over again, has proven useful enough that it hasn't needed to be expanded. So this is the CWE, Common Weakness Enumeration, and every year they and a couple other groups get together and they publish their list of top 25 most dangerous vulnerabilities. There's a bunch of other people who do it, but I think these are more readable and more useful than a lot of the others. You can get it at the cwe.mitre.org, top 25, whatever. These top 25 vulnerabilities represent the vast majority of real-world threats, the things that are actually going to be happening to your system. And so if you're able to rigorously protect against these or even seriously raise the bar on them, you're way ahead of your competition. You can get to a point where the vast majority of attackers aren't going to be able to successfully attack you. And the tiny fragment at the top, which are able to successfully attack you, are probably going to give a couple of tries at it. And if you're not a specific target for them, they're just going to move on. And so you've mitigated a lot of risk to your users, and you've stopped risk that you've already acquired from turning into harm to your users, which is kind of the whole goal. Since the top 25 it's too much to cover in one talk, we're actually just going to be focusing on 3 things in particular. And these happen a lot in real-world Python programs, so I think they're pretty relevant. We're going to talk about OS command injection. It's also called shell injection and a lot of other things. It's a really common sort of input sanitization flaw. And this basically happens either on the server side when you're trusting user input and using it to do some, passing it to the shell, or else you'll see it where you are distributing a script to a bunch of client machines and somebody uses your script as a vector to attack that client machine. Typically, in that case, your code is not the target, though. The second thing we're going to look at is cross-site scripting. And this is a web vulnerability. And basically, if you're a web developer and you don't know about cross-site scripting, odds are very, very, very good that you've got a cross-site scripting flaw. They've been utterly pervasive for the last couple of years, really for quite some time now. And they've proven very, very hard to spot. The good news is that there's a good set of tools that attackers use to find these things. And we can kind of turn that to our advantage. We can integrate those tools into our tests. And then the last thing that we're going to look at is we're going to look at path traversal or directory traversal. These aren't as common as they used to be. It used to be that basically every time you saw an upload form on the web, you saw a directory traversal vulnerability. People have gotten smarter about this, but they're still common enough, and there's still a couple of tricks that people can use that bypass some of the sort of stupid roll-your-own protection mechanisms. So let's go ahead and launch into it. Let's talk about command injection. This is sort of the archetype of what a command injection vulnerability looks like. In this case, you've just got this little list directory thing that's taking some attacker-provided input and concatenating it onto the end of this ls-la command. And it doesn't really matter that it's ls-la. Like the command itself is irrelevant. It could be ping. It could be anything else that you wanted. The important thing is that you've got attacker-provided input that's being passed directly to the shell, or even just with minimal blacklisting or whitelisting going on. So you can imagine that there's good input to this, which would make it pass a lot of functional tests, right? So I just pass MITRE to this, right? But you can also imagine that there's bad input to this, right? So in this case, your host. And this is going to be executed with whatever your privileges are normally. So whatever your program can do, it can do. Not a good situation to be in. Basically, attacker-controlled commands, not good. So the problem that a lot of people would have with this is, okay, so I know that it's bad, and I can look at it and I can say, well, all right, now I have no idea how to test for this because I have no idea what behavior actually triggers it. The first thing I would say, though, is that this is a pretty easy one to actually just remove, right? So instead of using get status output or get output or whatever, just don't call out to the shell, use exec, that sort of thing. It's not perfect protection, but it gets you a lot closer. Don't sanitize, construct if you can. Same thing's going to be true for XSS and a lot of other things. If you can possibly take a whitelisting approach rather than blacklisting approach, it'll work a lot better. But when it just can't be avoided, then yeah, testing's your only hope. And like I say, that's where people fall down. So the person who wrote this code in the first place probably doesn't understand that, like, maybe a semicolon is not something that I want to be taking. And they certainly don't understand that there's this sort of wide range of sort of a complete language that you can take and use to abuse this. So one of the tools that I like to look at in these cases is something called FuzzDB, and it's basically just a whole bunch of cases that have been provided either by attackers or penetration testers, and it's pretty much just there so that other tools can go through and not regenerate these lists of attacks on their own. Some of those tools are attacker tools, and some of them are actual good penetration test tools. And this is kind of a sample of this from their command injection. Files. And you can see what this is trying to do is it's trying to run ID. And so I guess I'm not sure if this is going to show up at all, but you can see it's just trying to evade a couple of kind of basic filters that you could do and all that sort of thing. And this is just part of a huge list of these. And what we're going to do is we're pretty much just going to build a little test harness so we can run over this. We can try our pretty stupid sanitizing routine against it. And see if anything fails, see if anything blows up. The only hard part in this is that we need to replace the ID in all this with something that we can instrument, so we can actually test, make sure that what we think is happening is happening. So we've replaced this with just a really stupid, simple thing here. It's just going to go ahead and create this create this file. And so after we've run through the whole list, or even at each point after I've tried a particular shell injection, I just test for the existence of this file. If I find that file, then I know that you failed. You can obviously do a lot smarter things than this, especially if you're trying to parallelize it or that sort of thing. That's not going to work. But it's not always necessary to do that. I actually haven't tested this code, so it may be a little bit janky, but this should be right in the essentials. Basically, all this is going to do is it's looking at this list of tests, which comes from FuzzDB. It's going to go through. It's going to iterate straight across that list of tests, every line in that list of tests, and try it out. See if it fails, and then say yes or no. Did I find this file? Boom. Okay, so that gives us a lot better test coverage, right? But how do we know that we no longer have a vulnerability here? What if somebody just left something kind of neato out of the FuzzDB thing? The bad news is that in an absolute sense we don't, right? Because we can't exhaustively test this. We can't be sure that there's not something inside of LS in this case where some particular input would wind up triggering badly, et cetera. The good news is that we've raised the bar a lot. So in the, excluding that sort of top tier of attackers who are probably going to get into your system no matter what, we've made it so that people who are using the same tools and people who are less intelligent than the tools that we're using basically can't successfully attack our code. And this is a big subset of attackers. So moving from OS injection over to XSS, if you're a web developer, this is basically the stupidest possible XSS. Please don't ever do this. If anybody uses this in real code, God have mercy. Basically, all we're doing here is we're just taking some unsanitized user input and we're inserting it directly into HTML. People actually do this. And in certain cases, like for really basic things, people just like clicking around on their computer. Yeah, sure, there you go, good input. My username works just fine. Okay, push it to production. But there's also the bad input, the obvious thing here being I'm just going to insert a couple of script tags. Oh, good, I get arbitrary JavaScript. Unlike the other attack, it's not that I'm compromising your server or whatever. I'm basically compromising every client you've got. So it lets me do things like fence posting. I can steal a lot of private data, and I can also launch attacks from places that I otherwise couldn't control. So you can imagine that somebody goes to this website, they load arbitrary malicious JavaScript, and they're inside of a corporate intranet. So they're on a machine that intranet trusts. You can imagine that pretty quickly escalates. And so this idea of like running attacker-controlled JavaScript, obviously you don't want it. And the problem is that most people, when they first see it, they go, wow, that's really bad. I should strip characters. I'm going to go ahead and I'm just going to pull out the opening and closing brackets, because then you can't put tags in, right? And tags are the real problem. No, tags are not the real problem. It doesn't work at all. If anybody who's a serious web developer uses it or suggests it, I just don't know what to say. You should use a real sanitizing library if you're forced to do this. Bleach is a pretty good example. Django has auto-escaping built in, so anything that winds up getting rendered automatically gets escaped. It's not perfect, but it's pretty good. It'll get you a long way towards being where you need to be. And this is kind of why I say that, like, stripping out certain characters and that sort of thing isn't going to work, because this is the second most obvious example of an XSS. You can see that this is just a case where instead of directly inserting something, they insert it as an attribute. And so we've got this possible good input. I actually don't know if that's good input or not. I wouldn't advise checking it on at work. But the obvious bad input is also there. So in this case, it's going to execute arbitrary JavaScript as soon as the mouse goes over this particular link. And so we wind up in the same place. We inserted a check for it, right? Like developer X got pwned. They inserted a check that stripped out these characters, and now they're in the same place as they were before. How is it that they want to actually gain a little bit more confidence in the result? How is it that they can get out of this hole that they're in? Besides like doing it right and using a serious library. And the way that you're going to wind up testing that is that you're, again, going to go back to FuzzDB. You're going to look at its giant list of XSS vectors, and it's just going to wind up iterating over those and trying each one of them out. It's super simple. It's basically exactly like what we had previous to this. But it does, again, require some instrumentation. The best way that I've seen to do this is basically that you'll insert JavaScript that calls out to a server. So you'll fire up simple HTTP server and say, OK, did I get any connections? Yes, no. And that'll tell you whether you had any failures on your test. One of the things about these sort of roll your own tests, though, is that frequently the attack tools are really, really good for a reason, right? Somebody actually spent the time to go out and write something like XSSer, which is one of my favorites. Not because like they found FuzzDB to be too strange or too hard to use or anything like that, but because they actually needed to test on a large scale, or they needed to test behavior that was common to a lot of different attack vectors. So in this case, XSSer was written as a tool to test HTTP and FTP connections, and so it's got a whole bunch of neat little things that you can put on there. Like you can specify, hey, here's the cookies I want, here's the headers I want, all that sort of thing. So if your web application requires that you have those in place, you can actually test end to end just by saying XSSer here, provide these cookies, provide these headers. And if you don't like XSSer, by the way, there's a link right there. If you don't like XSSer, there's probably 100 of other different fuzzers out there specifically looking at XSS. So there's a ton of these tools. Pick your flavor of the month. But they are really, really good, and they're quite effective. And you can get a bigger look at, or a bigger list of these attack tools at sectools.org. Actually, before we move on to this, so the thing that this gives us, the reason that we're interested in all this, is because by taking these tools and using them against our own site, we're effectively doing the same sorts of things that an attacker would do, except where they would find a vulnerability and exploit it, we would find a vulnerability and fix it. And so we put ourselves into a position where anybody using that tool, we've automatically knocked out. One of the consequences of that is that we do want to try and use more popular tools. So if you're in a position of depending on a relatively large stack of relatively popular components, things like Metasploit and Backtrack, they have a lot of tools in there to specifically attack those common components. And it's worth going after them in addition to doing this sort of specific spot testing. OK, so moving on to the directory traversal. The thing about this is the last two were basically just like toy demos. Like, hopefully you don't see examples of this kind of that kind of vulnerability in the wild as simple and easy to exploit as that anymore. You probably will, but hopefully you don't. This is a real world issue. And what this was in, it was in about a 90,000 line mashup of Python and C and Java that was designed to do some remote machine management. And as part of the sign-on process, there was this web front end which would accept RSA key, which it would then save at a client-provided location, which they trusted the web browser, never ever do that. At a client-provided location after some really simple verification. And so you can see kind of how this is working. You've got this user-provided path. I don't even know if you can see that over there. You've got this user-provided path, which is provided, they think, by the code that they have on the web browser. You have this user-provided data, which is supposed to be an RSA key. You're going to wind up placing, you're going to do this os.path.join to try and put this path on top of the user-provided path so that everything that somebody tries to save goes under that location. And then you're going to go through and do this check path, check data, all that sort of thing. So check path down here. It's going to try and take a possibly Erlang encoded value and decode it. And then it's going to try and save it. And then it's going to check for the ... So in case you don't know, I hope everybody here does. But if you did uploads /... it would take you up to the parent directory of uploads. So that would break out of this, ideally, sandbox that you've got here. And so as you can imagine, in something that's 90,000 lines and mashup of C and Python and all that sort of thing, and does remote machine management, the web front end was not really the primary focus. So that was not receiving a lot of the attention. But the upload functionality, we did kind of flag it and say, yeah, maybe we should run a fuzzer or something over this real quickly. And basically, here's what the fuzzer did. So it tried out this, pretty straightforward, ... all that sort of thing, trying to break out. And of course, the filter on ... caught that immediately. Later on, it tried this %2e being the Erlang encoding for a dot, %2e, %2e slash, %2e, %2e slash. Because we do that, the web.unquote there, that winds up getting caught. So we don't blow up on that either. But then it tried this other thing, this %252e, %252e. And that one wound up failing. And so that raises the question, what happened here? And basically, the problem here is that we unquoted twice. So you can see in check path, we've got web.unquote. And again, down in save, we've got another web.unquote. And this is basically just a problem where somebody wound up, at some point, this functionality was probably all centralized. There was probably some kind of bug, and they just refactored it out into some other place. And of course, it works on most normal input. But here you can see the %25 decodes to %2e encodes to dot. So we start out with %252e, %252e. We decode that, and it turns straight into %2e, which then on the second decode turns into ... And then we have a lot of fun because we can write things to all kinds of places. In this case, writing to cron.conf, which would normally be really super bad, wouldn't have been so bad because the check data actually did verify that it was a RSA key, at least as far as it could. But it still gave people the ability to clobber other people's authentication with random RSA keys, something that they provided, which of course was not the intent. So before we could go through and test this, we need to be able to instrument it. We need to figure out how it is that we can actually do this. And basically, you'll do it just like you would any other mocking library. So we're just going to wind up replacing the open built-in with something that says, please pass back out the value that you are actually asked to open. Once we've got that, we can just call the upload handler using something that we pull either from FuzzDB or from some other fuzzing tool. And then if the path that open actually tried to open was one that we wanted to permit, then we say, yes, you passed the test. And if not, no, then you failed the test. So it's pretty simple. It's not exactly difficult. And there's kind of a general pattern here, right? So you have you're going to go through, you're going to identify potentially interesting code. So this is code where either there's some kind of seam between the operating system and the program, or SQL and the program, or the web and the program, or possibly even just between Python and C. Then you're going to go through and you're going to check and see if it matches any of these sort of common attack patterns, right? So you're going to go onto CWE or that sort of thing and say, hey, what does this look like? Does this look like something that's been attacked a lot previously? Once you have that, that'll give you the information that you need to be able to basically just go through and Google for these attack tools. And once you have the attack tools, you can say either this is how they work, and you can integrate that behavior into your test, or you can even just directly integrate the behavior of the attack, or directly integrate the attack tools themselves, which is what we did in this case. Hopefully, you then wind up fixing the bugs, and then you repeat. You find another either interesting piece of code or another attack possibility and another attack tool. You integrate it, and on you go. And there's a ton of cases where this works really well, right? So pretty much all of the OWASP top 25, with the possible exception of bad credential handling, you can test this way. They're specific enough that you're going to be able to make some headway on it. And even if you aren't able to completely rule these attacks out, as you won't be able to, especially in the case of XSS, you're going to find so much of the low-hanging fruit, and you're going to find so many of these common attack vectors that you're going to make it so that less skilled attackers are just going to move on, and more skilled attackers, well, they were probably going to go ahead and get you anyway. And like I said, this is particularly good at finding that low-hanging fruit. So each one of these tests involving a fuzzer, it found when I ran through the last one, it wound up taking, I think, about 1.5 seconds to find the correct string to trigger the vulnerability. But there are some cases where this approach doesn't work, and basically that comes down to finding vulnerabilities which are not well known. So if there aren't good attack tools for it, then it's not going to work nearly as well. You're going to be in a pretty bad position, and you wind up with low confidence in the results of that test. Fuzzers in particular don't work well with large search spaces. You can imagine things like CSmith, which is a compiler fuzzer, where it pretty much has to generate the entire universe of C programs to be able to verify that compilers are behaving correctly. I think they've probably spent like the last 5 years generating these different test cases and running them through, and they've made a lot of good progress. They found a lot of bugs, and they've gotten a lot of them fixed, but at the same time they're still approximately as far away from finishing as they were when they started. It also doesn't work well on really hard to define problems. So if you're, for instance, using image recognition as part of a security critical path in your application, image recognition is like facial recognition and that sort of thing. It's pretty hard to really pin down when it's working and when it's not. It's really hard to automate. And so something like this, where you're trying to treat your tests as an oracle, you're trying to build your instrumentation into an oracle to tell you whether you're vulnerable or not under a particular test, it doesn't work so well. And then finally, you get into these heavily analytic problems. So a lot of sort of statistical attacks where it involves a lot of sort of tweaking parameters and that sort of thing before the vulnerability winds up popping out. It's not nearly as good in those situations either. So what I kind of hope that you've gotten out of this is that security testing really doesn't have to be that hard. I mean, the vast majority of these vulnerabilities they're pretty simple. There are good tools out there that were written by people who really know what they're doing to find them. It can be super, super effective, right? So ruling out big classes of adversaries, ruling out big classes of vulnerabilities in a big hurry, that's going to be much, much, much better than trying to do it yourself. And finally, that really you don't have to be that much of a security guru. You don't really have to know more than you would have to know to go on to CWE or OWASP and find the names of these vulnerabilities in order to be able to do this kind of testing. I guess that's it. Time for questions.
Great, thank you.
I have a question. It sounded like you were saying if you're going to be putting user input up on the web, you can't depend on fuzzers, et cetera. You have to do it right, but I didn't understand what doing it right was. Can you elaborate on that a bit?
So whenever you're dealing with purely user-generated input, you have to make sure that it's very, very tightly constrained, especially in a case like the web, where basically it's just one giant mashup of code and data. Getting it right, like specifically, would be many, many talks all by itself, but for sort of practical advice, use things like Bleach, use things like Django's auto-escaping. It's going to at least take you a long way towards being able to fend off the common attacks and even a lot of the more sophisticated ones.
I thought you were implying that those weren't the right solution.
No, sorry, I didn't mean to imply that.
Any more questions?
To the Ruby on Rails mass assignment vulnerabilities in any Python frameworks that you've come across?
So I haven't seen that. That doesn't mean it doesn't exist. My focus is primarily on cryptanalysis and things like that, though, so it wouldn't necessarily cross my desk.
Is there an effective way of doing automated testing, sort of like a continuous integration sort of testing for security vulnerabilities in a large website with multiple different inputs?
Yeah, so there's a lot of really, really good test suites that are out there. Things like Nessus, Burp is one that I think Burp has a free version now. And basically they're sort of a dime a dozen. They will set you back a lot of money for being a dime a dozen, but they're quite good. They're quite advanced.
Are there any open source versions that don't cost a fair amount?
Yeah, I mean, so if I recall, I think Burp is open source. No, I'm not certain about that, but I can look that up for you if you want. If you want to come by afterwards. No? Okay.
Is that W3AF? Is that?
Yeah, so I don't have any personal experience with it, but I hear good things about it. That may meet your needs. Sorry? I can give you a card afterward. Okay. Thank you guys very much.
It's okay.